Hey AP Advanced kids, in our last video on capacitors, we're going to talk about dielectrics. So what the heck is a dielectric? Well, what a dielectric is it's just an insulator that we put between the plates of a capacitor. So far we've talked about like air in between the plates of a capacitor, but that's not really realistic from a structure standpoint. So usually in between the plates are some sort of insulator. Now, what happens when we put an insulator in between charged plates? Well, here I have a little picture of the dielectric by itself, all right? No electric field, it's just an insulator, right? Now, I also have a picture here of a capacitor that doesn't have a dielectric, right? So if we charge up a capacitor, we get this electric field in between. And here we have it set up so the positive charges are on the left and the negative charges on the right. And so the electric field points to the right. Well, the dielectric, when we put it inside the capacitor, so if I take this and if I take that and I put it in there, what's going to happen is the electric field of the capacitor is going to cause polarization of the molecules in the dielectric. Now, it's not that the electrons can move. This is not a conductor. But what's going to happen is the molecules are going to all shift so that the electron clouds are attracted to the positive side of the capacitor, and that leaves an electron deficient side that's going to be on the negative side. And so we get this reverse electric field inside our capacitor. So here is a little picture of that. So here is my dielectric in here. And so the negative side is towards the positive plate, right? And remember that electric field lines point from positive to negative. And so because of that, I get this electric field due to the dielectric that points in the other direction compared to my original one. And so my new electric field that I have between these plates is going to be the sum of those two things, the original electric field without the dielectric and this reverse field due to the dielectric. So the net field, the new field, we could call it, is the difference between the old field and this new induced electric field in that dielectric. So we come up with a constant called kappa. Kappa is the ratio of the old electric field to the new electric field. So because of this, what happens, right, is we are going to, when we reduce the amount of the electric field inside, that's going to reduce the voltage, right? Remember the equation V is equal to E times D. So if the electric field goes down and the distance didn't change, that means my new voltage has to be less. And in fact, if we take a charged capacitor and we hook it up to a voltmeter and we measure the voltage, and then we slide a dielectric in there, we'll actually see that the voltage is going to decrease. And so this kappa, which is equal to the old electric field over the new electric field, is also the same in ratio, right? It has to be the same proportion of the old voltage to the new voltage. So the new voltage decreases, and experimentally, we can measure that. It's pretty cool. We're not making this stuff up. So even though the electric field decreases, the charge doesn't change, right? We didn't change the area of the plates. We didn't change the separation. And so the amount of charge on the plates is still the same. And therefore, if the electric field decreased and the charge didn't change, well, then the capacitance must be increased. And in fact, the kappa, if we take the kappa, that constant, we multiply by the original capacitance, we're going to get a new capacitance. So the capacitance is going to increase by the original capacitance times kappa. So a dielectric provides numerous advantages. One, it increases the capacitance of the capacitor. The second thing it does is it increases the operating voltage of the capacitor. So I can actually, there's certain voltage that a capacitor can handle, and when I put a dielectric in there, I can actually dial up the voltage before the capacitor breaks down. The second value of a dielectric is because it provides mechanical support. So it keeps those insulators from touching each other and discharging. So lots of advantages to having a dielectric. And in fact, every capacitor that you have has a dielectric inside it, like commercially. So one last thing, there is a maximum amount of electric field that the dielectric can handle before it breaks down. And so we call this dielectric strength. So how much the electric field that the dielectric can handle. And so if the electric field increases beyond its dielectric strength, so if I dial up the voltage too much, what's going to happen is that the dielectric breaks down. And so what actually happens is it like breaks down and it becomes a conductor and I kill the capacitor. So there's only so much voltage / electric field, electric potential, electric field that a dielectric can handle. And after that, it's kaput. So dielectrics are pretty cool. They're pretty useful, but even they have their limits. All right, let's do some work with dielectrics.